In the last video, I discussed some techniques for taking the integrals of complex trigonometric functions involving sine and cosine. And if you haven't watched those videos, I highly recommend you do, because it involves an explanation of how you take complex trigonometric integrals. Assuming you've watched it, I'm just going to start this video off by saying the heuristics, or the rules of thumb that we use to take tangent and secant functions. Now, tangent and secant functions are a lot harder to find the integral of than sine and cosine functions, and their rules of thumb are significantly more limited in their application. So the first rule of thumb that we need to learn to take these integrals is that if this power right here, if this n power is even, you will split off a secant squared, rewrite the remaining secant power as tangent power, and use a u substitution with tangent. So for a practical example, according to our rule, if this is even, we will break off a secant squared x. So this can be rewritten. Then we will rewrite the remaining secant function that we have broken it off of. We will rewrite that, right? We will rewrite that in terms of tangent. So I'm going to write that down here. Note, all I did when rewriting the secant squared x function was to substitute in the Pythagorean theorem for tangent and secant up here. I just substituted this in. Now I can simplify this expression, and my next step is to do a u substitution with tangent. And we can distribute this u and continue to solve the integral and then sub back in for tangent. That's also the reason why I've put these derivatives up here, just so you can memorize these and follow along with them. And I highly recommend that you commit these to memory. Now, the reason why I say that the tangent and secant rules of thumb are a lot more limited than the sine and cosine ones is because if you had a sine function, let's say, you could use your half-angle identities. But for secant and tangent, there's no such thing as a half-angle identity. Let's say that this was a 3. You could break off a sine x, rewrite this as cosine x, or in terms of cosine x, and then use a u substitution with cosine. But unfortunately, there's nothing that you could do that with in tangent or secant. And the main reason is because the derivative of sine is cosine, the derivative of cosine is negative sine, and so on. But the derivative of tangent is secant squared x, making it a lot harder to find these kinds of integrals. What this means is if you had an integral which looks something like this, you obviously couldn't break off any secant squared x, despite my secant here, though it's invisible, my secant here being a power of 0, right? I could just rewrite this as equal to tangent squared x secant 0x dx, right? This is the same thing. And over here my secant is an even number. However, I couldn't apply that even number rule. This means that in order for the even number rule to work, I guess you could assume that that n has to be some power greater than 2 that is even, so that you can break off a secant squared, or at least equal to 2. All this means is that you're going to have to work harder to find an integral when your rules of thumb don't work, and you may have to use different techniques. So the next rule basically says if your power of tangent, right, if your m over here, if m is odd, you want to isolate a secant times a tangent, rewrite the rest of your tangent functions in terms of secant, and then you want to use a u substitution of secant x. So I'll show you what I mean by this. Here we have a function that fits the bill, right? We have an odd power here, and so we're going to isolate a secant times a tangent, and I can rewrite this integral as, now, because I've isolated a tangent times a secant, I'm going to use a u substitution of secant x. And I'm not going to write the du because you can see it right here. The du would be secant x equals tan x secant x. So then I can rewrite this integral as, all I did here was I took my tangent squared x and I rewrote it in terms of secant squared x so that I could do a proper u substitution. And my du is just the derivative of u. And if my u is secant x, then my derivative is going to be tangent times secant. And that's the reason why we isolate that tangent and secant. Let's do another example with this odd power rule. So with this one I chose to do virtually the same example that I just did last time, but this time we don't have a secant. And this is mainly to demonstrate that the odd power rule is a little bit more forgiving than the even power rule, right? So what I could do here is I could multiply and divide by 1. This is a technique that we learned at the very beginning of advanced integration techniques. So this could be rewritten as, now What I did here was the first step I said, okay, I have an odd power right here, and if I have an odd power, I have to isolate a tangent times a secant. But because I don't have a secant in my equation, I have to get one. Therefore, in order to get one, I'm going to multiply by 1, which I'm going to have secant over secant, and then I can isolate a tangent times a secant. The next step of the odd power rule is to rewrite any remaining tangents in terms of secant. So I'm going to do that right now. So what I did right here is I didn't sub in my u's just yet, but I assumed that for a u substitution, I'm going to be using secant x. And if I'm going to be using secant x for my u substitution, then I know that my du is going to be equal to tan x secant x dx, right? So I got a tan x right here, I got a secant x right here, I got a dx right there. I can sub in my du. And now when I put in my u's, I get this. This is a very easy splitting fractions. In fact, I bet I've done this one in the splitting fractions video as an example. Now there's one last rule of thumb that you can use, and it essentially states that when the m, right, the power of the tangent is even, and the n, or the power of the secant, is odd, you can rewrite all tans as secants and then apply a reduction formula. And I'll show you the reduction formulas next, but I'll just give you one example here. So if we rewrite according to this rule, because this one's even and this one's odd, one of our options is to rewrite this tangent in terms of secant. And so I'm going to do that with the Pythagorean theorem right here. Right, tangent to the 4x is the same thing as tangent squared x squared. And then I sub in my tangent squared x right here. Now I can rewrite this entire expression as the integral of Alright, I expanded, and now I'm going to distribute my secant cubed x inside, so I'm going to get... Now this is where our reduction formulas come in, and if you watched the last video, you would have remembered that if I have, and I'm going to do this in a different color, if I have some power, or if I have some integral such that the sine is alone, or maybe let's say it's cosine, to any arbitrary power, right? I can reduce these with a specific reduction formula and continue breaking them down until I get a convenient integral that I can solve. And in a very similar manner, there are unique reduction formulas for tangent and for secant, which I'm going to write right now. So these are the two reduction formulas for tangent to some power and secant to some power. And I'm not going to completely solve this integral right here because it would take too long and you would lose track. But if I had to solve this integral on a test, what I would do is split it up into 3 parts, right? So we would have the integral of secant to the 7x minus the integral of 2 secant 5x plus the integral of secant cubed x dx, right? All of these would be in relation to x. And you can split those up. That's just one of your integral properties that you should remember. And then I would solve each one of these independently using the secant reduction formula. And I'm going to do one example just to show you how it would work using the last one, which is the easiest. So let's say that we have an integral, of secant cubed x. The reduction formula tells me that the first part would be the secant of n minus 2, and our n is 3 right here, so it would just be secant x times tangent x over 2, right? Remember, our n is 3, so n minus 1 is 2, plus n minus 2, our n is 3 again, so 1 over 2, the integral of secant n minus 2, so of secant x dx. And you would then have to take this one and try and use a different method to find the integral of secant x, multiply it by 1/2, and then add it. So if you're wondering where does cotangent and cosecant fit into this, it's actually very simple. It is the exact same thing and follows the exact same rules as the tangent m and the secant m n rules, right? The exact same. So for example, if my power was even, so if my power of n, right, if the power of the cosecant was even, I would split off a cosecant squared x and then try and rewrite the remaining cosecant in terms of the cotangent. And you can see the Pythagorean identities for each of these two pairs is virtually the same. The only difference comes in terms of the derivatives, right? So the derivatives of tangent and secant are slightly different. You have this negative. So for an integral, right, that looks the exact same as, an integral of cotangent and cosecant that looks the exact same as tangent and secant, it will likely end up just being a negative version with the cotangents and the cosecants replaced. So back to this idea that the cotangent and cosecant rules follow the tangent and secant rules. So if the cosecant, right, was of an even power, you'd want to split off a cosecant squared, rewrite the remaining cosecants in terms of cotangents, and then sub in a cotangent using U substitution. If the power of cotangent was odd, you would want to split a cotangent times a cosecant. You would want to try and isolate that, and in this case it would actually be negative, right, because the derivative of cosecant is negative cosecant cotangent. You would want to split off or isolate a negative cosecant times cotangent, and then you would want to do a U substitution using cosecant x. Now the only place where your rules would diverge from the tangent and the secant for cotangent and cosecant is that there aren't any convenient reduction formulas for cotangent and cosecant, unfortunately. So you would have to try and rearrange your integral in terms of tangent and secant so that you can use those more opportune reduction formulas. Now I'm going to do just one example to show you that these rules still do apply. So my rule tells me that if I have an n, which is an even power, right, then what I'm going to do is I'm going to split off a cosecant squared, right, which this is already isolated, and then I'm going to rewrite any remaining cosecant functions in terms of cotangent. Now there are no remaining cosecant functions because we've already isolated a cosecant squared. And then what I'm going to proceed to do is I'm going to use a U substitution, right, of cotangent x. Therefore, my du will be equal to negative cosecant squared x dx. But, as I mentioned before, because the derivatives of these functions are slightly different, the derivative of tangent is secant squared, but the derivative of cotangent is negative cosecant squared, my integral may become negative. So when I do my U substitution, right, my U is going to, this is going to become the integral of U squared, because I got my cotangent squared x, and my U is cotangent, times du. But my du is negative cosecant squared dx, and I only have a cosecant squared and a dx. Therefore, I have to multiply by negative 1 over negative 1 so that I can get that negative 1 right there, and so that they can cancel out equally, right? And that means I'm going to be left with a 1 over negative 1, which 1 over negative 1 is just negative. And so my integral is going to be the negative integral of u squared, which becomes the negative u cubed over 3, and I can sub back in my cotangent function, and I'll get negative cotangent cubed x over 3 plus c. Just like that, the problem is solved. So, to sum everything up that we've learned in this video so far, right, if my power of n is even, right, as long as this power of n is even, I'm going to want to split off a secant squared x and rewrite any remaining secants as tangent functions using my Pythagorean identity, which is why I recommend you memorize it. And then you're going to substitute in a tangent. That is the first rule. The second rule says if your tangent function has an odd power, right, if this m is odd, you want to be able to isolate a secant tangent, and then you're going to want to do a u substitution where u is equal to secant x. That's your second rule, right? And then your third rule says that if your m is even, right, and your n is odd, you want to rewrite all tangents in terms of secant. So again, you're going to be using your Pythagorean identity right here, and you want to apply your reduction formulas. And I wrote those. I'll write them one more time. Right, these are your reduction formulas. So for that third rule, you would want to simplify it as secants and then apply your reduction formula. Now, the cotangent and cosecant functions work the exact same way. The only difference is you need to constantly remember that these derivatives are slightly different. So most of your integrals, right, if you had the analogous version of tangent and secant, right, most of your cotangent, cosecant integrals would be the negative version of that. Furthermore, the cotangent and cosecant functions only the first two rules are applicable to cotangent and cosecant functions. But unfortunately, the third rule isn't very applicable because there are no convenient reduction formulas for cotangent and cosecant. And therefore, if you wanted to use reduction formulas, you'd have to write your cotangent and cosecant in terms of tangent and secant.